Welcome to Brain Vision.
So here we have a diagram of our rigid body. So let's assume that the angular velocity omega is equal to the magnitude omega, and the angular velocity is about the k-axis. So this is completely arbitrary. And the position vector g, which is this mass center relative to point A, so we have the mass center and we have point A, also has some magnitude r GA and is at an angle we'll call theta, as in this diagram here. So what this tells us is that the velocity of the mass center relative to position A, so VGA, is the angular frequency omega, the angular velocity, multiplied, or in this case cross, with RGA. And this is the magnitudes omega and the magnitude RGA at some other angle beta. But as we can see from here, that beta is simply theta plus this 90 degrees, the angle of 90 degrees. So we can see that beta is equal to theta plus 90 degrees. We also have that the velocity of the mass center, v bar, we know is equal to the velocity of point A, VA, plus the velocity of the mass center G relative to A. And finally, we can define a new vector H to be the position of the mass center R GA cross with the velocity of the mass center R VGA. So the cross product between the position and the velocity vectors. And so from above, we can see that we can simply write this as the magnitude R GA V GA in the k direction. And this is simply R GA squared times omega in the k direction, since omega is R times, so V is omega times R. And this is simply R of G with respect to A all squared times the vector angular velocity, omega. So using our definitions that we've provided above here, let's turn to looking at the system momenta, the momentum of the system of particles that make up our rigid body, and take moments about point A. So let's just draw this diagram. So we have our rigid body. Here we have point A, and here we have our center of mass, point G. We have a rotation, which is I bar, the centroid mass moment of inertia, times omega. And about the center of mass, which moves with momentum m v bar. So now we're looking at the center of mass point G, and we'll take moments about A. So moments about A, the sum of which we'll call capital H, is equal to R, the position of G relative to A, cross with m v bar, which is the momentum of the mass center, plus the angular momentum of I bar, the center, the mass center's moment of inertia, times omega, the angular velocity. So this angular momentum we can simplify using our definitions above. So this is R GA cross with M, and remember V bar we can write as VA plus VGA plus I bar omega. And we can expand this further to be R GA cross with M VA plus M R GA. So we're opening out the cross product, cross with VGA plus again I bar omega. So we just open out the cross product and we take the cross product of the two terms in the brackets. What we end up with is R GA cross with M VA plus M times the vector we defined as H, MH plus I bar omega. So this is equal to R GA cross with M VA, that term stays the same, plus M R squared G relative to A times vector omega plus I bar omega. So we're just substituting in for H. And this is simply the position vector of the mass center relative to point A crossed with the momentum M VA plus M R squared of G relative to A plus the center mass moment of inertia I bar, and we'll pull out the angular velocity omega as a common factor. So here we have our final expression for HA. Now, if we want the left-hand side to equal to I omega, we can get the first term on the right to equal to 0 if R, the vector, the position of the mass center relative to point A, is equal to 0, which simply means that A is the mass center. And that allows the first term to be 0. Or B, for the cross product to be 0, VA can be 0. which means that A is the instantaneous center of rotation. Or C, for another situation with this cross product, will be 0 is if R and V are perpendicular. So the position of the mass center relative to A is perpendicular to the velocity of A. If these two are perpendicular, the cross product becomes 0. Now, in the second term, we have the following. M R squared of the mass center with respect to A plus the moment of inertia of that mass center is equal to IA. So the moment of inertia at point A. And this is by the parallel axis theorem. So if mr squared GA plus I bar is equal to IA, we therefore have that the sum of the moments, or the angular momentum about point A, is equal to IA times the angular velocity omega. So for this to happen, we must have at least one of the conditions, A, condition B, or condition C, is satisfied. And this is the expression as we require.